Okay, so we are trying to find the area under a curve, not using geometry. We're going to use something called the Fundamental Theorem of Calculus. It's the biggest theorem in calculus for integration. Before we do that, let's talk about a little bit of where it came from. So before the Fundamental Theorem of Calculus, understanding how to find the area under a curve like this, they started with rectangles. So here, if you look, I have 4 rectangles under my curve. My curve is here. And they're called left endpoints because the left side of the rectangle is touching the curve itself, the function. You could also do it with right, where the right side is. So if I go back to left, you can see that this approximation is too small. My area approximation is too small. Here's the actual area down here. If I go to the right, my area approximation is too big because then the rectangles are bigger than the curve, taller than the curve. The midpoint probably gets you the best. It's the most efficient in there. And then what happened, they said, well, if we can approximate these little small pieces, what happens when I increase the number of rectangles? So this applet goes really fast, so I apologize. But if you can see here, as I increase the number of rectangles, they get smaller and smaller. That's that dx. That's this piece right here, the small piece. I get closer and closer to my actual area that I'm going to learn how to find today. So I could do that also with the right-sided or right endpoints. There's one rectangle. Obviously that doesn't work. But as I make the width of those rectangles smaller and smaller, or I increase the number of rectangles to infinity, like a limit, it gets closer and closer. Same here, I can start and I get closer and closer. So that's the theory behind finding this area under the curve. And if we were in class, in a classroom, I have a little lab with post-it notes that you actually make little rectangles and you figure that out. Hopefully that does it a little bit of justice. So today what we are going to actually look at is called the Fundamental Theorem of Calculus. And I'm going to just start by showing you something. This is right from the Cengage book, which you can get to, your ebook, which you can get to right from WebAssign if you ever want to look at that. Basically, the fundamental theorem puts derivatives and antiderivatives together. That's its purpose. Before now, derivatives are kind of their own little world, and integration was its own little world, the two branches of calculus. Well, the fundamental theorem ties them together to find the area under the curve. Just looking here, I don't know if you remember when we did open response, but I asked you like who was actually the father of calculus between Newton and Leibniz, and you guys had to decide who you thought. Again, they're both credited for this fundamental theorem independently, not together. So that's where it came from. That's the history again behind it in about 2 minutes. Which could take 3 classes, but it was in 2 minutes. So what we're going to do today is we're going to actually look at the fundamental theorem. So basically, how does differentiation, taking the derivative, and integration, the antiderivative, how do they become inverse operations? Because really they are inverse operations, and that's what we're going to look at today. You can kind of see here, again, this is a little visual. So first semester we worked just with derivatives, that tangent line. Remember we talked about a secant line and a tangent line. Well, the inverse of that is area. Here's area using rectangles, like I just showed you on the applet right here. And now we're going to find the area under the curve using the fundamental theorem of calculus. So the secant, the slope, is like the area of a rectangle. Both of these are something you could have figured out in algebra, in an algebra class without knowing any calculus. Tangent line, which is your derivative, and area under the curve, which is your antiderivative or your fundamental theorem of calculus, are something you need calculus for. And let's look at what it is. So again, it's tying derivatives and antiderivatives together and showing how they can be inverse operations. So let's first write down the fundamental theorem. So let's write this down. So you have the fundamental theorem of calculus states this. If you have an integral between a and b, so your boundaries are a and b, of f of x dx. So I'm looking for the area. So I'm just going to draw a real rough little sketch of what I'm talking about here. So here's this curve. It's a nice curve. I'm sure there's a function that defines that. And if I'm looking between a and b, how could I find this area without using a whole bunch of little rectangles or trapezoids or whatever shape you were using? Well, the relationship is that if you take the antiderivative of this function and you evaluate it at the upper boundary, b, and you then take that same antiderivative and you evaluate it at the lower boundary, a, and you subtract those two values, you get this area that we need. So remember that capital F stands for the antiderivative. So that is the fundamental theorem of calculus. It's the antiderivative evaluated at the upper boundary minus the antiderivative evaluated at the lower boundary. So it gives you the distance that, remember, distance is found by subtracting, so that's your a, your b minus a, and that distance in the antiderivative gives you that area. Usually somebody would raise their hand right now and say, well, what about c? What happened to plus c? I'll show that real quick. You don't have to write this in your notes. But if I took f of b plus c and I subtract f of a plus c, those constant terms would cancel. So that's what happened to that. All right, so let's try it. Let's try some. So we are going to figure out the area under this function, x squared minus 3. So this function is a parabola. It's -3 is its y-intercept. It looks like this. And we're going from 1 to 2. So how are we going to do that using the fundamental theorem? Well, we'll give it a try here. It says we're going to take our antiderivative. So the antiderivative of x squared is x cubed over 3. The antiderivative of minus 3 is minus 3x. And then we're going to evaluate that. And so when we show that we're evaluating the antiderivative using the fundamental theorem, you can use a bracket. Some people just use a vertical line. I usually use a bracket. And we're evaluating from 2 to 1. So then what you're going to do is now you're going to plug numbers in. So you're going to first put in 2. So if I put 2 in there, I would get 8 over 3 minus 6. That's my f of b. And then I'm going to subtract my f of a. And for a, I'm going to put in 1. So that would give me minus 1/3 minus 3. And from there, you're going to follow order of operations. So 8/3 minus 6. 6 would be 18/3, so that'd give me -10/3 minus 1/3 minus 3, that would give me -8/3. So if I add those, because it's two negatives, I'm going to get -2/3 for my area. So I'm going to bring back up the Desmos I used in a video a couple times ago. And we went from 1 to 2. And if you see right there, our area is -0.6 repeating, which is -2/3. Okay, so that is the fundamental theorem. We can try another one, and let's see what we got here. So again, first step is antiderivative. That would be 3x. Remember, this is a 1/2 power, So if we add 1, that's 3 halves. Divide by 3 halves, which if I rewrite that, that's just going to become 2x to the 3 halves, because those 3's would cancel. And you're going to evaluate that from 4 to 1. So if you put in 4, square root of 4, so you have 2 times 4 to the 3 halves. That's your f of b, minus 2 times 1 to the 3 halves. Let's see, this one, the square root of 4 is 2. 2 cubed is 8 times 2 is 16, minus, well, that's just going to be 2. So I get 14. Again, if you have the Desmos that I put on the one, you can go in here and check your answer. It's a great way to check your answer. I forgot our boundaries. It's 1 and 4, I think. And the answer is 14, and that is the answer we got. So again, these give us area. What's nice about them is definite integrals have an actual value answer, so they're really easy to check. You can do them with trig functions. We'll just go through this one quickly. The antiderivative of secant squared would be the tangent of x. And you're going to evaluate from pi over 4 to 0. You know, right now I'd be quizzing you on your unit circle. So you probably will need your unit circle when you're doing these. So you're going to have the tangent of pi over 4 minus the tangent at 0. The tangent at pi over 4 is 1. Again, you could put that in your calculator as well. Minus the tangent at 0, tangent sine over cosine, so that would give us 0. So my answer is 1. I'm not sure how well that one would work in the Desmos that I gave you. I can check it real quick. If I put in secant, equals secant squared of x. You'd have to approximate. You'd have to go in here and change this, but you could use it. Okay, so that is how you're going to do the antiderivatives using the fundamental theorem of calculus. And remember, you're finding area. Desmos will also check your answers. You can actually just open up a Desmos screen and use the, if you type in int, it'll give you your integration symbol. And you can type them in as well to check. All right, so check on the Canvas page, see what you need to do next.